Before Voyager 2 leaves our screens forever, it still has one final destination waiting in the darkness. Launched nearly 50 years ago, this tiny spacecraft has already crossed the giant planets, escaped the solar system, and entered the vast emptiness between the stars. But where will it go next? And what is the last place Voyager 2 will ever reach before time itself slowly erases every trace of its journey? Tonight, travel billions of miles beyond the sun and follow humanity's most distant explorer into the deepest future of space. If you enjoy relaxing space documentaries, don't forget to like this video, subscribe to the channel, and join us for more cosmic journeys beneath the stars. Far beyond the bright paths followed by the major planets, Voyager 2 continues its journey through a region of space that appears quiet, dark, and almost empty. The spacecraft travels farther from the sun each year, moving through distances that once existed only in calculations and imagination. From Earth, the spacecraft is now so distant that radio signals require many hours to cross the space between the two. Yet despite this separation, Voyager 2 remains part of the solar system. It occupies one of the most remote locations ever reached by a human-built object while still sharing a connection with the star that gave birth to every planet, moon, comet, and asteroid known in this neighbourhood of the galaxy. The solar system is often imagined as a collection of planets circling the sun. In reality, the planetary region occupies only a small portion of a much larger domain. The orbits of the giant planets lie deep inside an enormous volume of space, shaped by the sun's gravity and by material flowing outward from the sun itself. Voyager 2 has already passed every major planet it was designed to visit. Its encounters with Jupiter, Saturn, Uranus, and Neptune belong to an earlier chapter of its mission. Those worlds now remain far behind it, separated by distances so great that even the giant planets appear insignificant against the broader scale of the solar system. At its present location, Voyager 2 moves through a realm where sunlight is extremely weak. The sun still shines, but it no longer dominates the sky in the way it does near Earth. Seen from the spacecraft, the sun appears as an exceptionally bright star, rather than as a large glowing disk. Its light spreads across immense distances, becoming thinner and fainter with every outward step. The surrounding darkness is not unusual. Space itself contains vast regions where objects are separated by extraordinary distances. Voyager 2 now occupies one of those regions. The spacecraft itself remains remarkably small compared with the emptiness around it. Its instruments, antennas, and framework span only a few meters. Against the scale of interplanetary space, it is almost impossible to visualize. A tiny machine created on Earth during the 20th century now travels through a region larger than anything its builders could physically experience. The contrast between the spacecraft and its environment is one of the most striking aspects of the mission. Human engineering produces an object that can fit inside a building, yet that object crosses distances measured in billions of kilometers. Voyager 2 travels continuously. There are no engines pushing it forward. Its motion comes largely from energy gained during planetary encounters decades ago. During those encounters, the spacecraft uses the gravity of giant planets to alter its path and increase its speed. Gravity assists allow the mission to reach destinations that would otherwise require far more fuel than could be carried aboard. After completing those encounters, Voyager 2 continues onward, preserving much of the momentum acquired during its passage through the outer planetary system. The environment surrounding the spacecraft appears calm, but it is not completely empty. Individual particles move through space. Magnetic fields stretch across enormous distances. Radiation arrives from many directions. The density of matter is extremely low compared with anything familiar on Earth, yet physical processes continue. Instruments aboard Voyager 2 measure conditions that cannot easily be studied from within the inner solar system. These observations help scientists understand the outer reaches of the Sun's domain and the transition between different regions of space. From Earth, communication with Voyager 2 requires extraordinary technical effort. Powerful radio antennas send signals outward across billions of kilometers. The spacecraft receives commands and returns information using a transmitter whose power is modest by everyday standards. The signal arriving back at Earth becomes extremely weak after spreading across such immense distances. Sensitive receiving systems detect these faint transmissions and separate them from background noise. This communication link serves as a reminder that Voyager 2 remains connected to its place of origin even while operating in one of the most distant regions ever explored. Time behaves differently when viewed through the scale of the mission. human lives unfold across decades. Voyager 2 has already travelled for nearly half a century. Entire generations are born and grow into adulthood while the spacecraft steadily advances through the outer solar system. During that same period, the spacecraft experiences no dramatic changes in scenery. Distances between major objects remain immense. The pace of movement appears slow when measured against cosmic scales, yet it remains astonishing when compared with human travel. The spacecraft also serves as a historical artifact. Its technology reflects the engineering practices of the 1970s. Many of the components aboard Voyager 2 are older than a large portion of the world's population. Despite this age, the spacecraft continues operating far beyond its original expectations. Its survival demonstrates the durability of careful design and the advantages of a simple, robust architecture built for reliability. Engineers continue to manage the remaining resources with great care, extending the mission as long as possible. The position of Voyager 2 today represents the outcome of countless events. The formation of the solar system, the evolution of life on Earth, the development of science, and the growth of space exploration all contribute to the existence of this single spacecraft moving through deep space. Every measurement it returns adds another small piece to humanity's understanding of the wider environment surrounding the Sun. At this stage of its voyage, Voyager 2 occupies the distant frontier beyond the planetary realm. The familiar worlds of the solar system remain far behind. The spacecraft continues onward through a vast and sparsely populated region where sunlight is faint, matter is thin, and distance becomes the defining feature of existence. Within this enormous setting, a small machine from Earth quietly advances, carrying instruments, memories of planetary encounters, and a continuing connection to the world that launched it into the darkness. Beyond the distant region occupied by the planets, beyond the paths followed by Neptune and the scattered populations of icy bodies that circle the Sun at extraordinary distances, Voyager 2 continues to move through a domain still governed by a force that extends far beyond the reach of sunlight alone. The spacecraft remains inside the Sun's gravitational territory. Although it travels through darkness and isolation, it has not escaped the influence of the star at the centre of the solar system. The Sun's gravity reaches outward across distances so immense that the boundaries are difficult to imagine on a human scale. Gravity differs from light. Sunlight becomes fainter with distance and eventually appears little more than a bright point among countless stars. Gravity also weakens with distance, but it never truly ends. Every object possessing mass exerts a gravitational pull on every other object. The strength may become extremely small, yet the influence remains present. Voyager 2 experiences this pull continuously. Even at its remarkable distance from the Sun, the spacecraft remains connected to it through an invisible relationship established long before the spacecraft ever existed. The solar system is often described using the orbits of the planets because those worlds are easy to identify and measure. Yet the Sun's actual gravitational domain extends much farther than the planetary region. Countless icy bodies occupy remote areas far beyond Neptune. Some travel along elongated paths that carry them deep into the outer reaches of the solar system. Others remain so distant that they require thousands or even millions of years to complete a single orbit. These remote objects reveal that the Sun's influence reaches across a volume of space vastly larger than the region occupied by the major planets. Voyager 2 moves through this enormous gravitational landscape. Its trajectory is not a straight line in an absolute sense. Instead, the spacecraft follows a path shaped by the Sun's gravity, while also responding to the gravitational influence of the galaxy itself. The motion resembles a long, outward journey rather than an escape. The spacecraft possesses tremendous speed by human standards, yet cosmic distances are so great that even this speed allows only gradual progress across the broader structure surrounding the Sun. The Sun itself contains almost all the mass of the solar system. Because of this concentration of mass, its gravitational influence dominates the motions of planets, moons, comets, and spacecraft. Earth remains bound to the Sun, Jupiter remains bound to the Sun. Even distant icy objects continue to move under its control. Voyager 2 belongs to the same system. Although it no longer visits planets or conducts close encounters with major worlds, its motion still reflects the gravitational architecture established by the Sun. At great distances, the distinction between local and distant influences becomes more subtle. The Milky Way exerts gravitational forces on the solar system as a whole. Nearby stars contribute their own small effects, Giant clouds of gas and dust within the galaxy possess mass and therefore contribute to the overall gravitational environment. Yet within a vast surrounding region, the Sun remains the dominant local influence. This dominance creates an extensive sphere of control surrounding the solar system. Voyager 2 currently travels within that sphere. Understanding this immense scale requires abandoning familiar comparisons. Distances within cities, countries, and even across continents become insignificant. Light itself requires many hours to travel between Earth and Voyager 2. A journey by conventional aircraft would require an impossibly long time. Even the fastest spacecraft ever launched by humanity moves slowly when compared with the dimensions of the Sun's gravitational realm. The outer solar system represents a place where ordinary intuition no longer provides useful guidance. Scientists study the extent of the Sun's influence by examining the motions of distant objects. Comets offer particularly valuable information. Some originate from remote regions so far from the Sun that they spend most of their existence in darkness. Occasionally, gravitational disturbances alter their paths, sending them inward toward the planetary region. Their trajectories reveal the structure of the solar system's outermost domains. Observations indicate that the Sun's gravitational reach extends vastly beyond the locations explored by the planets and spacecraft. Voyager 2 gradually advances through this environment year after year. The spacecraft does not approach any known destination. Instead, it continues moving through a region defined primarily by distance itself. The Sun remains the central reference point. Every measurement of the spacecraft's position, speed, and direction ultimately relates back to that star. Even as the spacecraft moves farther away, the Sun remains the anchor of its journey. The concept of a final destination can sometimes be misleading when applied to deep space. Within the Sun's gravitational territory, Voyager 2 is not travelling toward a particular object. It is travelling through an immense structure whose scale extends far beyond ordinary experience. The spacecraft occupies one location within a vast gravitational system that contains countless unseen bodies, streams of material, and complex interactions accumulated across billions of years. From the perspective of celestial mechanics, the branch of science that studies motion under gravity, Voyager 2 represents an object following a predictable path through space. Scientists can calculate its future position with remarkable accuracy over long periods. These calculations reveal that the spacecraft remains part of the Sun's broader gravitational environment even while moving steadily away from the inner solar system. The outward journey continues, but the connection remains. The distant Sun still governs the fundamental structure surrounding Voyager 2. Its gravity shapes the overall framework within which the spacecraft travels. The planets occupy only a small inner portion of that framework. Beyond them lies an enormous expanse where the Sun's influence persists across staggering distances. In this vast territory, Voyager 2 continues its silent motion, carried forward through a region where gravity remains the defining force linking the spacecraft to the star from which its journey begins. Far from the planets and still within the broad domain shaped by the Sun, Voyager 2 moves through an environment that is influenced not only by gravity, but also by a continuous outward flow of matter. The Sun is not a quiet object resting at the center of the solar system. It constantly releases a stream of charged particles into space. These particles spread outward in every direction, forming a vast structure known as the heliosphere. A charged particle is an atom or subatomic particle that carries an electric charge and can respond to magnetic fields. The heliosphere surrounds the solar system like an enormous bubble, extending far beyond the orbit of the outermost planet. The existence of this solar bubble is not obvious from Earth. Human senses cannot directly perceive it. The particles are extraordinarily sparse compared with the atmosphere of a planet, yet the flow is continuous. Every second the Sun releases immense quantities of material into surrounding space. This material consists primarily of protons and electrons moving outward at high speeds. Together they form the solar wind, a stream that fills much of the solar system. Near the Sun, the solar wind is relatively dense and energetic. As it expands outward, it spreads across a larger and larger volume of space. The density gradually decreases, but the flow continues. By the time the solar wind reaches the region explored by Voyager 2, the particles are extremely sparse. Even so, they remain an important part of the environment. They carry energy, transport magnetic fields, and help define the structure of the heliosphere. The heliosphere is not a rigid shell. It is a dynamic region shaped by interactions between the outward flow from the Sun and the surrounding material of interstellar space. The Sun moves through the Milky Way, carrying the solar system along with it. As a result, the heliosphere exists within a larger galactic environment. The solar wind pushes outward, while matter from interstellar space presses inward. The resulting balance creates a vast bubble surrounding the Sun and its planets. Voyager 2 spends much of its mission travelling within this solar bubble. During its planetary encounters, the spacecraft moves through regions completely immersed in the solar wind. Even after passing Neptune and entering increasingly remote territory, it remains within the heliosphere for many years. Instruments aboard the spacecraft measure the properties of the surrounding particles and magnetic fields, providing valuable information about conditions that cannot easily be observed from Earth. The solar wind creates an environment that differs greatly from the emptiness often imagined in popular descriptions of space. Space is not completely vacant. Instead, it contains particles, radiation, and magnetic fields interacting across immense distances. The density may be extraordinarily low, but physical processes continue. Voyager 2 travels through a medium that is thin beyond ordinary experience, yet still capable of influencing the spacecraft and revealing important information about the Sun's reach. Magnetic fields play a central role within the heliosphere. The Sun generates a magnetic field that extends outward along with the solar wind. As the Sun rotates, this magnetic structure becomes twisted into a large-scale pattern that stretches throughout the solar system. Charged particles follow and interact with these magnetic fields. The result is a constantly changing environment influenced by solar activity, particle motion, and large-scale magnetic structures. The Sun itself undergoes cycles of activity. Periods of greater activity produce changes in the solar wind and the magnetic environment. Powerful eruptions on the Sun can send additional material outward through the heliosphere. Although Voyager 2 is extremely distant, these solar influences can still travel outward and affect conditions near the spacecraft. The effects may take many months or even years to arrive because of the vast distances involved, yet the connection remains. The heliosphere serves an important function beyond simply marking the extent of the solar wind. It also acts as a partial shield against certain forms of high-energy radiation arriving from elsewhere in the galaxy. These energetic particles, known as cosmic rays, originate from processes occurring beyond the solar system. The outward flow of the solar wind and its magnetic fields help reduce the number of some cosmic rays reaching the inner solar system. The shielding is not complete, but it influences the radiation environment experienced by planets and spacecraft. Voyager 2 provides scientists with an opportunity to study how this protective bubble behaves near its outer regions. Measurements reveal changes in particle densities, magnetic fields, and radiation levels as the spacecraft travels farther from the Sun. These observations contribute to a deeper understanding of how stars interact with the surrounding galaxy. The heliosphere represents the local example of a phenomenon that may occur around many other stars throughout the Milky Way. Despite its enormous size, the heliosphere remains finite. It is not an endless extension of the Sun's influence. The outward flow of solar material eventually encounters increasing resistance from the surrounding interstellar environment. As distance grows, conditions begin to change. The solar wind that moves rapidly outward from the Sun cannot continue unchanged forever. Physical processes gradually alter its behavior, creating regions where the character of the environment becomes different from that found closer to the Sun. For Voyager 2, the heliosphere forms the great ocean through which the spacecraft travels during the later decades of its mission. It is a realm of sparse particles, magnetic fields, and solar influence extending across extraordinary distances. Within this immense bubble, the spacecraft continues its steady outward motion, carrying its instruments through a region that remains connected to the Sun by a continuous flow of matter and energy. The heliosphere surrounds the journey, defining the environment in which Voyager 2 moves as it advances ever farther from the familiar planetary realm. As Voyager 2 continues through the outer reaches of the heliosphere, the environment surrounding the spacecraft gradually changes. The transformation is not sudden. It unfolds across an immense region where the outward flow from the Sun encounters increasing resistance from the material that fills interstellar space. This distant territory marks the outer portions of the solar bubble. Here, the conditions that dominate closer to the Sun begin to weaken, and the influence of the surrounding galaxy becomes more apparent. The solar wind begins its journey near the Sun at speeds far greater than the speed of sound within the surrounding plasma. Plasma is a state of matter in which atoms are separated into charged particles. Because the solar wind moves faster than disturbances can travel through this medium, scientists describe it as moving at supersonic speed. For much of the solar system, this rapid outward flow continues largely uninterrupted. Yet no expanding flow can continue forever without responding to the environment around it. Far from the Sun, the solar wind encounters pressure from interstellar space. This pressure does not resemble the pressure felt within Earth's atmosphere. Instead, it arises from extremely sparse gas, magnetic fields, and energetic particles occupying the region between the stars. Although the density of this material is very low, it extends across enormous distances. Over time, its cumulative effect becomes significant. The first major transition occurs at a region known as the termination shock. A shock in physics is a boundary where conditions change rapidly. At this location, the solar wind slows from supersonic speeds to slower speeds. The flow does not stop. It continues moving outward, but its character changes. The particles become compressed, temperatures rise, and the structure of the surrounding plasma becomes more complex. Voyager 2 crosses the termination shock during its outward journey. The crossing provides one of the most important opportunities ever obtained to study this distant region directly. Instruments aboard the spacecraft record changes in particle behavior and magnetic conditions. These measurements confirm that the spacecraft has entered a new environment unlike the regions explored during its encounters with the giant planets. Beyond the termination shock lies a broad region called the heliosphere. This area forms the outer layer of the heliosphere. The solar wind still dominates, but it no longer flows freely as it does closer to the Sun. Instead, the particles move more slowly and interact more strongly with the pressures coming from outside the solar bubble. The heliosphere can be imagined as a transition zone where the Sun's outward influence begins to lose its ability to push aside the surrounding interstellar medium. The heliosphere is extraordinarily large. Even a spacecraft traveling as rapidly as Voyager 2 requires years to cross it. Within this region, conditions vary from place to place. Particle densities change, magnetic fields shift, energetic particles move through the environment in complex ways. Observations indicate that the outer heliosphere is not perfectly smooth or symmetrical. Instead, it possesses structure shaped by the interaction between solar activity and the broader galactic environment. The Sun itself contributes to these variations. Solar activity changes over time, altering the strength and properties of the solar wind. Disturbances originating near the Sun can travel outward through the heliosphere and eventually reach the heliosphere. By the time these effects arrive, years may have passed since the events that create them. The immense scale of the heliosphere means that changes propagate slowly across its full extent. Within the heliosphere, Voyager 2 detects increasing numbers of energetic particles that originate beyond the solar system. Some of these particles penetrate deep into the heliosphere. Others interact with magnetic structures near the outer boundary. Their presence provides clues about the relationship between the solar bubble and the wider galaxy. Scientists use these observations to refine models describing how charged particles move through space. Magnetic fields become particularly important in this distant region. The magnetic field carried outward by the solar wind becomes compressed and distorted as external pressures increase. The resulting structures influence the motion of charged particles throughout the heliosphere. Because magnetic fields are invisible, their presence must be inferred through measurements. Voyager 2 serves as a rare observer embedded directly within this environment. The heliosphere also demonstrates that boundaries in space are often broad transition zones rather than sharp dividing lines. Conditions evolve gradually across vast distances. One region blends into another through continuous physical processes. The outer heliosphere illustrates this principle clearly. There is no visible wall marking the limit of solar influence. Instead, there is a long and complex region where competing forces interact. For scientists, the heliosphere represents a natural laboratory. Similar processes likely occur around other stars throughout the galaxy. Many stars release winds of charged particles into surrounding space. Where those stellar winds meet the interstellar medium, structures analogous to the heliosphere may form. Voyager 2 provides direct evidence that helps researchers understand these universal interactions. The farther the spacecraft travels through the heliosphere, the more apparent it becomes that the environment is changing. The outward dominance of the solar wind weakens. External influences grow stronger. Particle populations shift. Magnetic conditions evolve. The region serves as the final outer layer of the solar bubble before a more profound transition takes place. Voyager 2 spends years moving through this vast boundary zone. The spacecraft remains connected to the Sun through the continuing flow of particles and magnetic fields, yet the character of the surrounding environment steadily changes. The heliosheath stands as the distant frontier of the heliosphere, a region where the Sun's influence encounters the pressures of the galaxy beyond. Within this immense transition zone, Voyager 2 advances patiently through a changing sea of particles and fields, carrying humanity's instruments toward the outermost edge of the solar bubble. After years of travel through the heliosheath, Voyager 2 approaches one of the most important boundaries ever crossed by a human-made object. This boundary is known as the heliopause. It marks the location where the outward pressure of the solar wind is no longer strong enough to dominate the surrounding environment. Beyond it lies interstellar space, the region between the stars. The heliopause is not a wall, nor is it a visible surface. It is a transition created by the balance of physical forces acting across enormous distances. The concept of a boundary in space can be difficult to imagine because there are no solid markers. The heliopause exists because two environments meet. On one side is the solar wind carrying particles and magnetic fields outward from the Sun. On the other side is the interstellar medium, the sparse gas and magnetic environment that fills the galaxy between stars. Where these influences reach equilibrium, the heliopause forms. For many years, scientists seek to understand exactly where this boundary lies and how it behaves. Theoretical models provide estimates, but direct measurements remain essential. Voyager 2 carries instruments capable of studying charged particles, magnetic fields, and plasma. These instruments allow the spacecraft to detect changes in its surroundings and reveal when it moves from one environment into another. As Voyager 2 nears the heliopause, observations begin to show important changes. The number of particles originating from the solar wind decreases. At the same time, particles associated with interstellar space become more prominent. The balance shifts gradually rather than instantly. The spacecraft records evidence that the outermost region of the heliosphere is giving way to a different environment. One of the most significant indicators comes from plasma measurements. Plasma, the electrically charged gas that fills much of space, behaves differently on either side of the boundary. Inside the heliosphere, plasma originates largely from the Sun. Beyond the heliopause, plasma belongs primarily to the interstellar medium. Differences in density and behavior help scientists identify the transition. In the year 2018, Voyager 2 crosses the heliopause. The event represents a historic milestone in the exploration of space. The spacecraft becomes only the second human-made object known to enter interstellar space directly. Its observations confirm that it has moved beyond the solar wind's dominant influence and into the broader environment of the galaxy. The crossing provides a unique scientific opportunity because Voyager 2 carries a functioning plasma instrument. This capability allows direct measurement of conditions during the transition. The data reveal a clear increase in plasma density beyond the heliopause, consistent with expectations for interstellar space. These observations strengthen confidence in scientific understanding of the boundary and the environments on either side. Although Voyager 2 enters interstellar space, it does not leave the solar system in the broader gravitational sense. The Sun's gravity still extends far beyond the heliopause. The spacecraft remains within the Sun's gravitational domain while simultaneously occupying interstellar space. This distinction is important. The heliopause marks the edge of the heliosphere, not the end of the Sun's gravitational influence. The magnetic environment also changes across the boundary. Measurements show differences in the behavior of magnetic fields before and after the crossing. Yet the transition proves more subtle than some early models predict. The magnetic field beyond the heliopause does not point in a dramatically different direction. Instead, the observations suggest a more complex relationship between solar and interstellar magnetic structures. The heliopause itself is not fixed permanently in one location. Conditions within the heliosphere change as solar activity rises and falls. The pressure exerted by the solar wind varies over time. As a result, the exact position of the boundary can shift. The heliosphere expands and contracts in response to long-term changes in solar conditions. Voyager 2 happens to encounter the heliopause at one particular moment in this ongoing process. Crossing into interstellar space does not produce a dramatic visual transformation. the spacecraft does not suddenly encounter bright stars, dense clouds, or unusual objects. The surrounding region remains dark and sparsely populated. The difference lies primarily in the physical properties of the particles and fields surrounding the spacecraft. Scientific instruments detect these changes even though human eyes would notice little difference. The achievement nevertheless carries deep significance. For the first time, humanity obtains direct measurements from beyond the heliosphere. Observations made by Voyager 2 allow scientists to compare conditions inside and outside the solar bubble. These comparisons improve understanding of how the Sun interacts with the galaxy and how stellar winds shape their surrounding environments. The crossing also highlights the extraordinary longevity of the mission. Voyager 2 launches in the year 1977, with objectives centered on the outer planets. Decades later, the spacecraft continues operating far beyond those original goals. Its instruments remain capable of collecting valuable information from one of the least explored regions accessible to direct observation. Beyond the heliopause, the spacecraft enters a new phase of its journey. The outward flow of solar wind no longer defines its immediate surroundings. Instead, Voyager 2 becomes a traveler within the interstellar medium itself. The transition marks the end of one environment and the beginning of another. The solar bubble remains behind, while the vast space between the stars surrounds the spacecraft on every side. Within this quiet and sparsely populated region, Voyager 2 continues forward, carrying human knowledge beyond the edge of the heliosphere and into the broader galaxy. Beyond the heliopause, Voyager 2 travels through a region known as local interstellar space. The spacecraft no longer moves within the solar wind that fills the heliosphere. Instead, it occupies the broader environment that exists between the stars of the Milky Way. This new setting appears quiet and empty, yet it possesses its own structure, composition, and physical processes. The change is not dramatic in appearance. Darkness still surrounds the spacecraft. Distances remain immense. The stars continue to shine as distant points of light. The difference lies in the nature of the medium through which Voyager 2 now passes. Interstellar space is often described as a vacuum. In everyday language, this description seems reasonable because the density of matter is extraordinarily low. Yet it is not completely empty. A small number of atoms, charged particles, dust grains, and magnetic fields occupy the space between stars. The density is so slight that a volume comparable to a room on Earth would contain almost nothing at all. Nevertheless, when this sparse material extends across trillions upon trillions of kilometers, it becomes an important component of the galaxy. Voyager 2 now moves through this medium. The particles surrounding the spacecraft are no longer primarily supplied by the Sun. Instead, they belong to the interstellar environment itself. These particles originate from many sources. Some come from ancient clouds of gas that persist between stars. Others result from material expelled by dying stars long ago. The interstellar medium represents a mixture accumulated over billions of years of galactic history. One of the most important differences beyond the heliopause involves plasma density. Measurements indicate that plasma is more abundant in local interstellar space than in the outermost heliosphere. The density remains extremely low by terrestrial standards, yet it exceeds the levels found immediately inside the heliopause. This increase helps confirm that Voyager 2 has entered a distinct physical environment. The spacecraft also detects changes in the population of energetic particles. Within the heliosphere, solar influences shape the radiation environment. Beyond the heliopause, the balance shifts. Cosmic rays become more prominent. Cosmic rays are highly energetic particles traveling through the galaxy at enormous speeds. Many originate from powerful astrophysical events such as supernova explosions, where massive stars end their lives and eject material into surrounding space. These particles move across vast distances and contribute to the energetic environment of interstellar space. The magnetic field surrounding Voyager 2 remains an important subject of study. Magnetic fields exist throughout the galaxy, although they are generally weak compared with those encountered near planets or stars. Even weak magnetic fields influence the motion of charged particles. Observations from Voyager 2 provide direct information about the local magnetic environment and help scientists understand how magnetic structures are organized within the nearby galaxy. Temperature within interstellar space presents an interesting challenge for interpretation. Individual particles may possess considerable energy, corresponding to temperatures that seem surprisingly high. Yet because the density is so low, The total amount of heat present remains extremely small. A spacecraft travelling through this environment does not experience temperature in the same way an object would within a dense atmosphere. The sparse particles seldom collide with the spacecraft. As a result, the surrounding medium can be described as energetically active while still appearing almost empty. Voyager 2 serves as a unique scientific observer in this region. Very few instruments have ever operated directly within interstellar space. Remote observations from Earth reveal much about the galaxy, but direct measurements provide information that cannot be obtained in any other way. The spacecraft continues transmitting data that help refine understanding of local interstellar conditions. The distances involved remain extraordinary. Even after crossing the heliopause, Voyager 2 is not approaching another star in any meaningful sense. The nearest stars remain immensely far away. Interstellar space is defined largely by separation. Stars may appear close together when viewed from Earth, but the actual distances between them are vast beyond ordinary comprehension. Voyager 2 enters this environment not as a visitor nearing another system, but as a traveller beginning a journey through an immense expanse. The local interstellar medium is not uniform. Density, composition, and magnetic conditions vary from place to place. These variations occur across scales ranging from relatively small regions to enormous galactic structures. Scientists seek to understand how such differences arise and how they influence the evolution of the galaxy. Measurements from Voyager 2 contribute valuable information to this effort. The spacecraft itself remains a tiny object moving through a vast ocean of sparse matter. Its antenna continues pointing toward Earth. Its instruments continue operating as long as power remains available. Every signal received from Voyager 2 carries information about a region that humanity can study directly only through this distant explorer. The data arrive slowly after crossing billions of kilometers, yet they provide an ongoing connection between Earth and interstellar space. The transition into local interstellar space represents more than a geographic milestone. It marks the beginning of direct exploration of an environment that fills much of the galaxy. While planets and stars attract attention because of their visible presence, the interstellar medium occupies the enormous spaces between them. Understanding this medium is essential for understanding the galaxy itself. Voyager 2 now travels within that broader setting. The solar wind no longer dominates its surroundings. The spacecraft moves through sparse gas, energetic particles, and faint magnetic fields belonging to the interstellar medium. Darkness remains the prevailing visual impression, yet the environment contains a rich array of physical processes. Within this quiet region between the stars, Voyager 2 continues its steady journey, carrying human instruments through a realm that until recently could only be studied from afar. Within local interstellar space, Voyager 2 moves through a medium that appears almost empty, yet contains the raw materials from which stars, planets, and future generations of cosmic structures emerge. The region surrounding the spacecraft is filled with interstellar gas and dust distributed so thinly that the human mind struggles to imagine it. Nevertheless, this sparse material plays a fundamental role in the life of the galaxy. It forms the background environment through which stars travel and from which new stars are eventually born. The majority of interstellar matter consists of gas. Hydrogen is the most abundant element in the universe and also the most common component of the interstellar medium. Helium follows as the second most abundant element. Smaller amounts of heavier elements are present as well. These heavier elements originate from earlier generations of stars. Through processes occurring within stellar interiors and during stellar deaths, atoms such as carbon, oxygen, silicon, and iron become dispersed into the galaxy. Over immense spans of time, this material mixes with the surrounding gas. The density of interstellar gas remains extraordinarily low. In many regions, only a few particles occupy a volume that would seem completely empty under terrestrial conditions, yet space is vast. Even such sparse material becomes significant when spread across distances measured in light years. Entire clouds containing enormous amounts of mass can exist while remaining almost invisible. Voyager 2 travels through one small part of this larger environment. Its instruments detect particles that reveal the character of the surrounding medium. Each measurement helps scientists understand conditions within the nearby interstellar region. Although the spacecraft samples only a narrow path through space, the information it collects provides valuable insight into the structure of the galaxy immediately surrounding the solar system. Interstellar dust forms another important component of the medium. Dust grains are tiny solid particles composed of heavier elements. Many are smaller than grains of smoke. Some consist largely of carbon-rich compounds. Others contain silicates, materials related to the minerals found in rocks. These particles originate through a variety of astrophysical processes. Dying stars release dust into space, while supernova explosions distribute additional material throughout the galaxy. Despite their small size, dust grains influence the appearance and evolution of the Milky Way. Dust absorbs and scatters light, creating dark regions visible within astronomical images of interstellar clouds. Dust also participates in chemical processes. The surfaces of dust grains provide locations where atoms can interact and form simple molecules. In this way, tiny particles contribute to larger cycles of galactic evolution. Voyager 2 is unlikely to encounter large concentrations of dust. The medium surrounding the spacecraft remains extremely diffuse. Still, dust is present as part of the broader environment. Over immense periods, even sparse dust populations can affect objects moving through interstellar space. The effect on Voyager 2 during the foreseeable future remains negligible because collisions are extraordinarily rare. The vastness of space ensures that most particles remain separated by great distances. Gas and dust do not remain stationary. They move under the influence of gravity, magnetic fields, shock waves, and galactic motion. Some material drifts slowly through the galaxy. Other regions experience disturbances produced by stellar activity. Over millions of years, these processes reshape the distribution of matter. Clouds form, evolve, and disperse. New stars emerge from dense regions, while dying stars return material to the interstellar medium. The composition of interstellar gas provides a record of cosmic history. Hydrogen traces back to the early universe. Many heavier elements originate within stars that lived and died long before the formation of the Sun. Every atom drifting through the medium possesses its own history. Some may have passed through multiple generations of stars before becoming part of the local interstellar environment. The material surrounding Voyager 2 therefore represents not only a physical medium but also a repository of galactic memory. Scientists study interstellar gas using several methods. Telescopes observe light emitted or absorbed by atoms and molecules. Spacecraft provide direct measurements of local conditions. Together, these approaches reveal a medium that is far more complex than an empty void. Different regions possess different temperatures, densities, and chemical compositions. Some areas contain cold clouds where molecules can survive. Others contain hotter gas energized by nearby astrophysical events. Voyager 2 occupies a region where the interstellar medium is relatively diffuse. The spacecraft does not travel through a dense cloud. Instead, it moves through sparse material characteristic of the local galactic neighborhood. Measurements help establish the properties of this environment and provide a reference point for broader studies of the Milky Way. The interaction between gas, dust, magnetic fields, and radiation creates a dynamic system. Light from stars passes through interstellar matter and influences its behavior. Charged particles respond to magnetic fields. Shock waves from distant stellar explosions compress and disturb clouds. These processes operate continuously across the galaxy. Although the effects near Voyager 2 may appear subtle, they belong to a larger network of interactions shaping the evolution of interstellar space. From a human perspective, the medium surrounding Voyager 2 seems almost perfectly empty. Yet scientific observations reveal a different reality. Sparse atoms drift through the region. Dust grains move silently across vast distances. Magnetic fields thread through the gas. Radiation travels between the stars. Together, these components form the interstellar medium, the material filling the spaces that separate stellar systems. As Voyager 2 advances through local interstellar space, it becomes immersed in this diffuse mixture of gas and dust. The spacecraft continues to sample particles that originate not from the Sun, but from the wider galaxy. These observations provide a direct glimpse into the substance occupying the immense regions between stars. Within this quiet environment of sparse matter and subtle processes, Voyager 2 continues its journey through one of the fundamental components of the Milky Way. Within the broad expanse of interstellar space, the region surrounding Voyager 2 is not entirely random or uniform. The spacecraft currently travels through a specific portion of the interstellar medium known as the local interstellar cloud. This cloud is not a cloud in the familiar sense of something dense and visible floating across a sky. Instead, it is a vast region of sparse gas and dust occupying part of the galaxy near the solar system. The cloud extends across distances so immense that even light requires years to cross significant portions of it. The solar system itself moves through this cloud. The Sun is not stationary within the Milky Way. Along with its planets, moons, comets, and spacecraft, it travels around the centre of the galaxy. As a result, the solar system passes through different interstellar environments over immense spans of time. At present, scientific observations indicate that the Sun and its surrounding heliosphere occupy a region embedded within the local interstellar cloud. Voyager 2 now shares that environment. The cloud consists primarily of hydrogen and helium, the most abundant elements in the universe. Trace amounts of heavier elements are present as well. The material remains extraordinarily diffuse. The density is vastly lower than even the thinnest atmosphere found on a planet. Yet compared with some other regions of interstellar space, the local interstellar cloud contains a measurable concentration of matter. Scientists investigate the cloud using a combination of spacecraft measurements and astronomical observations. Light from nearby stars passes through the cloud before reaching Earth. By studying how certain wavelengths of light are absorbed, researchers can estimate the cloud's composition, density, temperature, and motion. Voyager 2 contributes direct measurements from within this broader environment, providing information unavailable through remote observation alone. The temperature of the local interstellar cloud is relatively warm by interstellar standards. Individual particles possess enough energy to correspond to temperatures of several thousand degrees, yet the density remains so low that the cloud contains very little total heat. The concept differs greatly from everyday experiences of temperature on Earth. A region may have particles moving with substantial energy, while still feeling effectively empty because collisions occur so rarely. The cloud is not perfectly homogeneous. Variations exist in density, ionization, and composition. Ionization refers to the process by which atoms gain or lose electrons and become electrically charged. Radiation from nearby stars influences these conditions. Magnetic fields also affect the structure of the cloud. Together, these factors create subtle differences across different portions of the region. Voyager 2 travels through only a tiny fraction of the cloud. Even after many decades of flight, the spacecraft covers only a minute distance compared with the full dimensions of the surrounding interstellar environment. This reality highlights the immense scale of galactic structures. Human-made spacecraft can travel for generations and still remain within a single local region of the galaxy. The origin of the local interstellar cloud remains an area of scientific investigation. Observations suggest that it may be connected to larger structures shaped by ancient stellar activity. Over millions of years, supernova explosions and stellar winds can rearrange interstellar gas, creating cavities, shells, and clouds of varying density. The local interstellar cloud likely forms part of this larger and evolving galactic landscape. One notable feature of the cloud is its interaction with the heliosphere. The heliosphere does not exist independently of its surroundings. The pressure, density, and magnetic properties of the local interstellar cloud influence the size and shape of the solar bubble. If the solar system occupied a different interstellar environment, the heliosphere might possess different dimensions and characteristics. Thus, the cloud plays a direct role in shaping the boundary region that Voyager 2 crosses before entering interstellar space. The cloud also participates in the larger cycle of matter within the Milky Way. Gas drifting through interstellar space may eventually become incorporated into denser regions where new stars form. Material expelled from older stars becomes mixed into the cloud. Over immense periods, atoms migrate through different phases of galactic evolution. The hydrogen surrounding Voyager 2 today may one day contribute to the formation of future stars or planetary systems. From the perspective of the spacecraft, however, these processes unfold across timescales far longer than its mission. Voyager 2 experiences the local interstellar cloud as a quiet environment of sparse particles and weak magnetic fields. The spacecraft continues moving steadily through the cloud, collecting data about the immediate conditions around it. Every measurement helps refine understanding of the local galactic neighborhood. The cloud also serves as a reminder that interstellar space contains structure. The region between stars is not an empty void lacking organization. Instead, it contains clouds, cavities, magnetic fields, and varying concentrations of matter. The solar system occupies one such region at the present time. Voyager 2 now provides direct observations from within that environment. Astronomers continue studying nearby interstellar clouds because they influence the conditions experienced by the solar system. As the Sun moves through the galaxy, it may eventually encounter different regions with different properties. Such changes occur over timescales measured in tens of thousands or millions of years. The local interstellar cloud represents only one stage within a much longer galactic journey. For Voyager 2, the cloud forms the immediate setting through which it travels after leaving the heliosphere. The spacecraft advances through a diffuse mixture of gas and dust that surrounds the solar system itself. This local interstellar neighbourhood remains sparse, quiet, and nearly invisible, yet it possesses its own history, structure, and role within the Milky Way. Within the vast dimensions of the local interstellar cloud, Voyager 2 continues its slow progression through the galaxy, sampling the environment that now surrounds both the spacecraft and the distant Sun from which it began its journey. Beyond the local interstellar cloud lies the broader stellar neighbourhood of the Sun. Voyager 2 continues its journey through interstellar space, but the spacecraft is not travelling through an empty wilderness devoid of stars. It occupies a small region within a vast population of stellar systems distributed throughout the Milky Way. The stars nearest to the Sun form a local community, separated by immense distances yet sharing the same general galactic environment. From Earth, the night sky creates the impression that stars are scattered across a distant surface. In reality, they occupy a three-dimensional structure extending through space in every direction. Some are relatively nearby on a galactic scale. Others lie hundreds, thousands, or tens of thousands of light-years away. Voyager 2 remains deep within the Sun's local neighbourhood, a region containing numerous stars with a variety of sizes, temperatures, ages, and histories. The nearest star system to the Sun is the triple star system known as Alpha Centauri. Even this closest stellar neighbour lies more than 4 light-years away. Light, moving at the fastest speed known in nature, requires more than 4 years to cross the distance. Voyager 2 travels at a speed remarkable by human standards, yet it would require many tens of thousands of years to cover such a span. This comparison reveals the extraordinary scale separating even more neighbouring stars. The stars surrounding the Sun are not evenly distributed. Some regions contain somewhat greater concentrations, while others are relatively sparse. The local stellar neighbourhood includes red dwarfs, which are small and comparatively cool stars as well as larger stars possessing different physical characteristics. Red dwarfs are especially common throughout the Milky Way. Many of the stars nearest to the Sun belong to this category. Each nearby star possesses its own history. Some form billions of years before the Sun. Others emerge later from interstellar clouds that collapse under gravity. Over time, stars convert hydrogen into helium within their cores, gradually evolving according to their masses. The stellar neighbourhood therefore represents a collection of objects existing at different stages of development. Voyager 2 travels through the space between them, never approaching close enough to observe most of them in detail. Astronomers map the positions and motions of nearby stars with increasing precision. Observations reveal that stars are not fixed in place. Each one follows its own path around the centre of the Milky Way. Their motions are generally slow when viewed over a human lifetime, but over thousands or millions of years the changes become significant. The stellar neighbourhood is therefore dynamic rather than static. Distances between stars gradually change as they move through the galaxy. The Sun participates in this motion as well. Together with its planets and spacecraft, it orbits the galactic centre. Voyager 2 shares that larger movement. Although the spacecraft travels outward relative to the Sun, both remain embedded within the broader flow of galactic motion. The local stellar neighbourhood evolves continuously as stars drift through space along their individual trajectories. Many nearby stars possess planetary systems. Observations over recent decades demonstrate that planets are common throughout the galaxy. Some stars host giant planets larger than Jupiter. Others possess rocky worlds comparable in size to Earth. The existence of these systems transforms the view of the local stellar environment. What once appears as a collection of isolated stars now emerges as a population of complex systems containing diverse worlds. Despite this richness, the distances remain overwhelming. Voyager 2 is not heading toward a nearby planetary system in any practical sense. The spacecraft's trajectory carries it through interstellar space, but the separation between stars is so great that encounters remain exceedingly rare. The local neighbourhood contains many stars, yet they are spread across a volume of space almost beyond comprehension. The brightness of stars can also be misleading. Some nearby stars appear relatively faint because they are intrinsically small. Others seem brighter because they emit more light. Distance and luminosity together determine how stars appear when viewed from afar. Voyager 2 observes essentially the same stellar skeeks seen from the outer reaches of the solar system, with only subtle differences caused by its changing position. The region surrounding the Sun belongs to a larger structure within the Milky Way known as the Orion Arm, a minor spiral arm segment containing many stars and interstellar clouds. The local neighbourhood forms only a tiny portion of this immense galactic architecture. Nevertheless, understanding nearby stars provides an important foundation for understanding the galaxy as a whole. Their distances can be measured with greater accuracy than those of more remote stars, allowing astronomers to construct detailed maps of the surrounding region. Scientific observations indicate that the stellar neighbourhood has changed significantly over the history of the solar system. Stars that are nearby today may not have been nearby in the distant past. Likewise, future configurations will differ from present ones. The local environment remains in constant motion, shaped by the orbital dynamics of the Milky Way. Voyager 2 now travels through this broader stellar setting. The spacecraft remains far closer to the Sun than to any other star, yet it occupies the interstellar medium shared by neighbouring systems. Around it lies a vast population of stars moving through the galaxy, each carrying its own history and physical characteristics. Within this local stellar neighbourhood, Voyager 2 continues its quiet journey through all the space that separates one star from another, advancing slowly through a region defined not by emptiness alone, but by the immense distances linking countless stellar systems across the Milky Way. Within the local stellar neighbourhood, Voyager 2 continues its motion at a steady pace. The spacecraft travels farther from the Sun each year, yet the meaning of that motion changes when viewed against the immense timescales of the cosmos. Human history is measured in generations. Civilizations rise and fall over centuries. Recorded history spans only a few thousand years. Voyager 2 already operates on a timeline that stretches beyond many human institutions. Its future journey extends much farther still, unfolding across intervals that greatly exceed the lifespan of any individual civilization. The spacecraft was launched during the 20th century. Since that time, societies change, technologies advance, and entire generations come and go. Meanwhile, Voyager 2 continues moving through space with remarkable consistency. The spacecraft does not experience the passage of time in the same way that human societies do. It follows physical laws that remain unchanged whether decades or millennia pass. Its trajectory evolves gradually, shaped by gravity and motion rather than by the events occurring on Earth. Considering the future path of Voyager 2 requires a shift in perspective. Distances between stars are so vast that ordinary human timescales become insufficient. Even after thousands of years, the spacecraft will have travelled only a fraction of the distance separating neighbouring stellar systems. 1,000 years is a substantial period in human history. Empires emerge and disappear within such intervals, yet on the scale of interstellar travel, 1,000 years represents only a brief segment of the voyage. 10,000 years extends even farther beyond familiar experience. Human languages evolve dramatically over such periods. Cultures transform. Entire landscapes may change under the influence of climate and geology. During the same interval, Voyager 2 continues its outward motion through interstellar space. The spacecraft covers an impressive distance, yet the nearest stars remain remote. The scale of the galaxy ensures that even many thousands of years produce only gradual progress. As time extends into hundreds of thousands of years, the contrast becomes even more striking. Geological processes that seem slow today become increasingly important. Coastlines shift, mountain ranges erode, species appear and disappear. The arrangement of stars in the night sky also changes because stars move through the galaxy along their own paths. Constellations familiar to observers on Earth gradually lose their recognizable forms. The celestial patterns seen today are temporary features within a constantly evolving stellar environment. Voyager 2 participates in this long-term evolution. The spacecraft does not remain fixed relative to the surrounding stars. Its own motion contributes to the changing geometry of the local galactic neighbourhood. Over hundreds of thousands of years, the spacecraft occupies locations far removed from its current position. Yet even then, it remains only a tiny traveller within an enormous stellar population. Astronomers often use deep time to understand cosmic processes. Deep time refers to intervals so long that ordinary historical comparisons become inadequate. Stars evolve over millions or billions of years. Galaxies change over similar spans. Voyager 2 offers an interesting example because its projected future can be calculated across remarkably long intervals. The spacecraft follows predictable physical laws, allowing scientists to estimate its motion far into the future. These calculations reveal a journey extending beyond the duration of modern civilization. Long after communication with Earth ends, Voyager 2 continues moving through interstellar space. Long after its instruments cease operating, the spacecraft remains in motion. The end of the mission does not mean the end of the voyage. Instead, the spacecraft becomes a silent object traveling through the galaxy according to the momentum acquired during its planetary encounters decades ago. The contrast between operational life and physical existence is important. The mission depends on electrical power, functioning instruments and communication systems. Those capabilities are limited. The spacecraft itself, however, can survive far longer. Interstellar space contains very little matter capable of causing significant damage over short timescales. As a result, the structure of Voyager 2 may persist for extraordinarily long periods. Time also affects the stars surrounding the spacecraft. Nearby stars continue their own journeys around the Milky Way. Some eventually move closer to the Sun's region of the galaxy. Others drift farther away. The local stellar neighborhood observed today is therefore only a temporary arrangement. Over hundreds of thousands of years, entirely different stars may become the nearest neighbors of the solar system. The Milky Way itself evolves slowly. Its spiral structure rotates. Gas clouds move and interact. New stars form while older stars reach the ends of their lives. Against these processes, Voyager 2 remains a small participant carried along by galactic motion. The spacecraft is not traveling through a static backdrop but through an environment undergoing continuous change. Human imagination often seeks destinations, arrivals, and endings. Yet the timescales relevant to Voyager 2 reveal a different reality. The spacecraft spends most of its future not arriving anywhere but traveling. Its journey is defined less by specific locations than by the passage of immense intervals of time. Thousands of years become milestones. Hundreds of thousands of years become meaningful units for describing future encounters and positions. Viewed against deep time, Voyager 2 occupies a unique place in human history. It is both a product of a particular era and a traveller whose motion extends far beyond that era. Civilizations may transform in ways impossible to predict, while the spacecraft continues following its trajectory through interstellar space. The immense timescales involved reveal the true scale of the galaxy and the challenge of travelling between stars. Within this framework of deep time, Voyager 2 advances steadily onward, carrying the legacy of its origin into a future measured not in generations, but in vast stretches of cosmic history. As Voyager 2 continues through interstellar space, its future path can be projected far beyond the timescales of human history. Astronomers use measurements of the spacecraft's speed, direction, and position to estimate where it will travel over tens of thousands and even hundreds of thousands of years. These calculations reveal that Voyager 2 will pass through various regions of the local stellar neighborhood. Although the spacecraft is not intentionally heading toward any particular star, the motions of both the spacecraft and nearby stars create future encounters that can be estimated with reasonable confidence. A close stellar passage in astronomy differs greatly from the everyday meaning of closeness. Even when a spacecraft passes near a star by astronomical standards, the actual separation remains immense. Distances are still measured in trillions of kilometers. The stars remain remote points of light rather than destinations that can be reached directly. Nevertheless, such encounters provide useful reference points for understanding Voyager 2's long-term journey. The motion of stars through the Milky Way is an essential part of these calculations. Every star possesses its own velocity and direction of travel. Over thousands of years, these motions gradually alter the arrangement of the stellar neighborhood. A star that is distant today may move closer in the future. Another that is currently nearby may drift away. Because Voyager 2 and the stars are all bound for moving, future approaches depend on the combined motion of multiple objects rather than on the spacecraft alone. Current scientific estimates indicate that Voyager 2 is likely to pass relatively near several stars over the coming hundreds of thousands of years. One of the most frequently discussed examples involves the star known as Ross 248. This small red dwarf is projected to become one of the closer stellar encounters along the spacecraft's future path. Yet even during this approach, the distance between the spacecraft and the star remains vast. The encounter represents a near passage only in the context of interstellar scales. Red dwarf stars play an important role in discussions of future stellar encounters because they are extremely common throughout the Milky Way. These stars possess lower masses and lower luminosities than the Sun. Many remain stable for extraordinarily long periods, often far exceeding the expected lifetime of the Sun itself. Their abundance means that spacecraft travelling through the local stellar neighbourhood are statistically more likely to pass near red dwarfs than near larger and brighter stars. Voyager 2's future path also illustrates the difference between travel and arrival. The spacecraft is not designed to slow down upon reaching another stellar region. It carries no propulsion system capable of changing its course significantly. Instead, it continues moving along a trajectory determined largely by the gravitational interactions that occur during its encounters with the giant planets decades ago. Any future stellar passage therefore represents a flyby rather than a destination. The distances involved remain extraordinary. Even after hundreds of thousands of years of travel, Voyager 2 will still occupy only a tiny portion of the Milky Way. The galaxy spans roughly 100,000 light-years across. Against this scale, the spacecraft's future movement appears modest. Nevertheless, from a human perspective, the projected journey is immense. It extends beyond recorded history, beyond modern civilization, and far beyond the duration of the mission itself. Astronomers calculate future stellar encounters using increasingly precise measurements of stellar motion. Observatories map the positions and velocities of nearby stars with remarkable accuracy. These data allow researchers to reconstruct past configurations of the stellar neighbourhood and estimate future ones. While uncertainties increase over longer timescales, the general picture remains clear. Voyager 2 will continue moving through a changing stellar environment shaped by the motions of countless stars. The spacecraft itself will almost certainly remain silent during these future passages. Long before any close stellar encounter occurs, its power supply will have been exhausted. Its instruments will no longer function. No signals will travel back to Earth. Yet the spacecraft will continue its physical journey. It will remain a small artifact from Earth, travelling through interstellar space, long after its operational life has ended. Future stellar approaches also emphasize the emptiness of the galaxy. Even in regions containing many stars, the average separation between systems remains enormous. The probability of a direct collision with a star is effectively negligible. Spacecraft such as Voyager 2 can travel for millions of years without encountering anything resembling a planetary system at close range. The galaxy contains vast numbers of stars, yet the spaces between them dominate its volume. The stars that Voyager 2 may pass in the future are themselves dynamic objects. Some host planetary systems, others possess magnetic activity, stellar winds, and complex histories of formation and evolution. The spacecraft will never investigate these systems directly. It will simply pass through the broader environment of the galaxy, while the stars continue along their own independent paths. These projected encounters provide useful markers along an otherwise open-ended journey. They allow scientists to describe the spacecraft's future position relative to recognizable astronomical objects. Without such reference points, the voyage becomes difficult to visualize because interstellar space lacks obvious landmarks. The stars serve as signposts within a vast and mostly empty environment. Voyager 2 therefore continues toward a future defined by motion rather than arrival. Over hundreds of thousands of years, it will pass through different regions of the local stellar neighbourhood and experience distant encounters with nearby stars. These passages remain scientifically interesting, yet they do not represent the end of the journey. The spacecraft will continue onward, moving through the galaxy long after its brief encounters have come and gone. Within the immense timescales of interstellar space, each stellar approach becomes only a momentary event along a path that stretches far into the future. As Voyager 2 moves beyond the immediate scale of nearby stars and future stellar encounters, it remains embedded within a much larger structure. The spacecraft travels through a small region of the Milky Way, a galaxy containing hundreds of billions of stars, vast clouds of gas and dust, dark matter, magnetic fields, and complex patterns of motion. The local stellar neighbourhood occupies only a tiny fraction of this enormous system. To understand the broader environment surrounding Voyager 2, it becomes necessary to view the spacecraft within the context of the galaxy itself. The Milky Way is a spiral galaxy. Its stars are arranged within a flattened disk that contains winding spiral structures extending outward from the central regions. The Sun occupies a position far from the galactic center, residing within a minor spiral arm segment often called the Orion Arm. Voyager 2 remains extremely close to the Sun on galactic scales. Even after decades of travel, the spacecraft has moved only a minute distance compared with the dimensions of the galaxy. The Milky Way spans roughly 100,000 light-years from one side of the disk to the other. Its thickness varies, with the central regions being more concentrated and the outer portions becoming thinner. Within this immense structure, spheres orbit the galactic center under the influence of gravity. The Sun participates in this motion, completing one orbit around the center of the Milky Way in approximately a few 100 million years. Voyager 2 shares this larger journey because it remains gravitationally associated with the solar system's general motion through the galaxy. The galactic center lies tens of thousands of light-years away from the Sun. Observations indicate that a supermassive black hole occupies the very center of the Milky Way. Around this central region, stars, gas clouds, and other material move in complex patterns. Voyager 2 remains far removed from these crowded inner environments. The spacecraft travels within a comparatively calm outer portion of the galactic disk, where stellar densities are lower than those found near the center. Interstellar gas and dust are distributed unevenly throughout the Milky Way. Some regions contain dense molecular clouds capable of forming new stars. Others consist of large cavities where previous generations of stars have altered the surrounding environment. The local region around the Sun belongs to one such relatively sparse area. Voyager 2 therefore travels through a part of the galaxy characterized by moderate stellar density and diffuse interstellar material. The galaxy also contains magnetic fields extending across enormous distances. These fields influence the motion of charged particles and contribute to the structure of the interstellar medium. Although weak compared with magnetic fields near planets or stars, galactic magnetic fields remain important components of the larger environment. Voyager 2 moves through regions shaped in part by these subtle yet widespread influences. One of the most significant discoveries in modern astronomy involves the presence of dark matter within galaxies. Dark matter is a form of matter inferred through its gravitational effects. It does not emit, absorb, or reflect light in a way that can be directly observed with current instruments. Observations indicate that dark matter contributes substantially to the total mass of the Milky Way. The motions of stars and gas throughout the galaxy suggest that visible matter alone cannot account for the observed gravitational behavior. Voyager 2 travels through a region influenced by this larger gravitational framework. Although the spacecraft cannot directly detect dark matter, its motion occurs within a galaxy whose structure is shaped by both visible and invisible components. The Milky Way therefore represents a far more complex system than a simple collection of stars scattered through space. The spiral structure of the galaxy is also dynamic rather than permanent. Stars do not remain fixed within individual spiral arms. Instead, they move through the galactic disk, while large-scale density patterns help maintain the appearance of spiral structure. Over immense spans of time, stars migrate through different regions of the galaxy. The Sun itself has likely occupied various galactic environments during its long history. Voyager 2's future journey unfolds within this changing framework. The spacecraft is not merely traveling between stars. It's moving within a galaxy that continuously evolves through gravitational interactions, stellar birth, stellar death, and the circulation of interstellar matter. Every atom of gas surrounding the spacecraft participates in larger galactic cycles operating across millions and billions of years. From the perspective of the Milky Way, Voyager 2 is almost unimaginably small. The spacecraft measures only a few meters across. The galaxy spans distances so vast that even entire planetary systems become tiny components within its structure. Yet the spacecraft carries scientific significance because it allows humanity to directly sample one small part of the interstellar medium embedded within this larger galactic environment. The stars visible from Earth belong to the same galactic system through which Voyager 2 travels. Their distribution, motions, and histories are connected to the broader evolution of the Milky Way. The spacecraft occupies a position within this immense network of stars and interstellar matter, sharing the galaxy's motion around its center. Seen on a galactic scale, Voyager 2 remains very near its point of origin. Decades of travel become almost insignificant against the dimensions of the Milky Way. Yet the spacecraft continues moving through a real and evolving environment shaped by stellar populations, interstellar clouds, magnetic fields, and the gravitational influence of visible and invisible matter. Within the vast structure of the Milky Way, Voyager 2 advances quietly onward, a small traveller crossing one tiny portion of a galaxy whose scale extends far beyond the reach of any human journey. Within the immense structure of the Milky Way, Voyager 2 continues its outward journey. Yet when the spacecraft is viewed against the full scale of the galaxy, a striking reality becomes clear. The distances involved are so vast that there are limits to what the spacecraft can ever reach. Although Voyager 2 is one of humanity's most successful explorers, its future path illustrates the enormous challenge of moving between stars and across the galaxy. The spacecraft will travel for millions of years, but even that extraordinary duration is not enough to carry it through more than a tiny fraction of the Milky Way. Human intuition develops within a world where journeys are measured in kilometers and days. Even interplanetary travel, while difficult, remains understandable within the span of a human lifetime. The galaxy operates on a completely different scale. The nearest stars lie several light-years away. The Milky Way itself spans roughly 100,000 light-years. Distances of this magnitude transform the meaning of travel. Voyager 2 moves at a speed that would seem astonishing in any terrestrial context. It covers vast distances each year, yet the spacecraft does not travel at a significant fraction of the speed of light. Because of this, the journey between stars requires enormous amounts of time. The spacecraft's motion is sufficient to leave the planetary region and enter interstellar space, but it is not sufficient to rapidly cross the galaxy. Even over hundreds of thousands of years, Voyager 2 remains within the local stellar neighbourhood. Future close passages by nearby stars represent only small movements across the broader galactic map. The spacecraft continues advancing, yet the galaxy remains overwhelmingly larger than the distance it can cover. This reality is not a limitation of engineering alone. It reflects the fundamental scale of cosmic structures. The Milky Way contains hundreds of billions of stars. Many possess planetary systems. Countless worlds likely orbit within the galaxy. Yet Voyager 2 will never visit more than a tiny number of stellar environments. Its trajectory carries it through interstellar space rather than toward a sequence of destinations. The probability of a meaningful encounter with a planetary system remains extremely small because stars are separated by such immense distances. The vast majority of the galaxy will therefore remain forever beyond the reach of Voyager 2. Entire spiral arms, star-forming regions, globular clusters, and distant stellar populations lie far from its path. The spacecraft is not travelling toward the galactic centre. It is not heading toward a major cluster of stars. Instead, it follows a narrow trajectory through one limited region of the galactic disk. Astronomers can project this motion far into the future. Over millions of years, Voyager 2 continues moving relative to nearby stars. Yet the galaxy itself is also changing. Stars orbit the galactic centre. Interstellar clouds drift and evolve. New stars are born while others die. The environment through which Voyager 2 travels never remains completely fixed. Even so, the spacecraft cannot keep pace with the immense scale of these larger processes. The concept of a destination becomes increasingly difficult to define under such conditions. A destination implies arrival at a specific place. Voyager 2's future contains many positions and future encounters, but no final target chosen by design. The spacecraft is not programmed to reach another star system. Its journey continues because motion persists in the absence of significant resistance. The spacecraft travels onwards simply because nothing substantial exists to stop it. Collisions are extraordinarily unlikely. The space between stars is so empty that Voyager 2 can travel for immense periods without striking a large object. Individual particles and occasional dust grains may interact with the spacecraft, but the probability of encountering a planet, star, or other major body remains effectively negligible. The galaxy contains many objects, yet the volume separating them is vastly greater. This emptiness helps explain why Voyager 2 can survive for such long durations. Interstellar space provides little opportunity for catastrophic impacts. The spacecraft gradually ages, but it does not face the hazards associated with moving through dense environments. Its structure may therefore persist for very long periods while continuing along its trajectory through the galaxy. The limits of Voyager 2's journey also reveal an important truth about space exploration. Reaching interstellar space is a remarkable achievement, but reaching another star remains a much greater challenge. The gap between those accomplishments reflects the enormous scale of the cosmos. The spacecraft demonstrates both humanity's capability and the vastness of the environment being explored. Future civilizations, if they exist, may develop technologies capable of traveling much faster than Voyager 2, yet the spacecraft itself remains a product of its era. It carries the momentum acquired during its planetary encounters and continues along a path determined by the physics of that moment. Its future is therefore largely fixed. It can travel onward, but it cannot fundamentally change the scope of its journey. Seen from this perspective, Voyager 2 becomes a reminder of the true dimensions of the Milky Way. The spacecraft leaves the planets behind, crosses the heliosphere, enters interstellar space, and continues toward distant stellar encounters. Yet even after accomplishing all of this, it remains within a tiny corner of the galaxy. Most of the Milky Way lies beyond its reach. The spacecraft's path extends across immense distances by human standards, but against the scale of the galaxy it remains a narrow thread passing through one small region of a structure far larger than any journey it can ever complete. As Voyager 2 continues its journey through interstellar space, the spacecraft itself gradually changes. The surrounding galaxy remains vast and enduring, but the machine carrying humanity's instruments cannot operate forever. Every system aboard Voyager 2 depends upon finite resources. The mission that begins with planetary exploration eventually enters a stage defined not by distance alone, but by the slow decline of the spacecraft's ability to generate power, operate instruments, and communicate with Earth. Voyager 2 does not rely on solar panels. At its present distance from the Sun, sunlight is far too weak to provide useful electrical power through conventional solar energy systems. Instead, the spacecraft uses radioisotope power systems. These devices generate electricity from the natural decay of radioactive material. The process produces heat, which is converted into electrical energy. This technology allows spacecraft to operate in regions where sunlight is insufficient for practical use. The radioactive material aboard Voyager 2 decays steadily over time. This decay is predictable and continuous. As the years pass, the amount of available power gradually decreases. Engineers understand this process from the beginning of the mission. The spacecraft is designed to function for as long as possible while managing an increasingly limited energy supply. Throughout its operational life, mission controllers make careful decisions regarding power consumption. Instruments are turned off when necessary. Systems that are no longer essential are reduced or shut down. These measures help preserve electricity for the most valuable scientific observations. The process resembles managing a slowly diminishing reserve, where each decision affects how long the mission can continue. Communication requires energy as well. Voyager 2 uses a radio transmitter to send information back to Earth. The signal must travel across billions of kilometers, becoming extraordinarily weak by the time it arrives. Large radio antennas on Earth detect these faint transmissions. Maintaining this connection becomes increasingly challenging as the spacecraft grows more distant and available power declines. The spacecraft's instruments also face limitations. Scientific instruments are designed for long-term operation, but no technology functions indefinitely. Electronic components age. Exposure to radiation gradually affects materials. Temperature changes influence performance. Engineers monitor these factors carefully, seeking ways to extend the useful life of the spacecraft for as long as possible. Despite these challenges, Voyager 2 demonstrates extraordinary durability. Many of its systems continue operating decades beyond their original expectations. The spacecraft survives in part because interstellar space is relatively benign compared with environments near planets possessing thick atmospheres, strong magnetic fields, or intense radiation belts. The sparse conditions of interstellar space reduce certain types of wear and damage. Eventually, however, available power becomes insufficient to support active operations. As electrical output decreases, instruments must be turned off one by one. Each shutdown reduces the spacecraft's scientific capabilities. The mission gradually transitions from a fully functioning observatory to a more limited platform. Over time, fewer systems remain active. A point will ultimately arrive when communication can no longer be maintained. The transmitter requires power, and without sufficient electricity, signals can no longer be sent to Earth. When that moment occurs, Voyager 2 becomes silent. No further scientific data will arrive. Commands from Earth will no longer reach the spacecraft in any meaningful way. The operational mission will come to an end. The loss of communication does not mean the destruction of the spacecraft. Voyager 2 will remain physically intact. Its antenna, instruments, and structural components will continue traveling through interstellar space. The spacecraft simply ceases functioning as an active scientific mission. It becomes a silent artifact moving through the galaxy. The distinction between mission life and physical existence is significant. Mission life depends upon power and communication. Physical existence depends upon the survival of the spacecraft itself. Interstellar space contains very little matter capable of causing rapid deterioration. As a result, Voyager 2 may remain recognizable for extraordinarily long periods. Small impacts from microscopic particles may gradually alter surfaces, but major damage remains unlikely over relatively short astronomical timescales. The famous record carried aboard Voyager 2 will also continue its journey. The spacecraft contains a gold-plated phonograph record designed to convey information about Earth and humanity. It includes sounds, images, and music selected to represent aspects of life on Earth. Although the probability of another civilization ever encountering the spacecraft remains extremely small, the record serves as a symbolic message carried into interstellar space. Over thousands and even millions of years, Voyager 2 will drift through the galaxy as a silent object. No instruments will operate, no signals will be transmitted. Yet the spacecraft will remain a physical trace of human activity. Long after the societies that build it have changed, the spacecraft may continue its journey through interstellar space. The future condition of Voyager 2 therefore differs from its present state. Today it remains an active explorer, collecting measurements and communicating across immense distances. In the future it becomes something else, a dormant traveller carried forward by momentum alone. The transition is gradual rather than sudden. Instruments fall silent one by one. Power decreases steadily. Communication eventually ends. Within the vast environment of the Milky Way, Voyager 2's operational life represents only a brief phase of its existence. The active mission occupies decades. The silent voyage that follows may endure for periods vastly longer. As the spacecraft continues through interstellar space, its role changes from scientific observer to enduring artifact. The machine that once explored planets and crossed the heliopause gradually becomes a quiet remnant of humanity's early ventures into the wider galaxy, continuing onward long after its final transmission has faded into silence. After the instruments fall silent and communication with Earth ends, Voyager 2 continues moving through the Milky Way. The spacecraft no longer functions as an active mission, yet its journey persists. At this point, the question of a final destination becomes more difficult to answer. Human experience often assumes that every journey ends somewhere. Roads lead to cities, ships reach ports, aircraft arrive at airports. Interstellar space operates according to different rules. For Voyager 2, the future is defined less by arrival than by continued motion through an immense and evolving galaxy. The phrase final destination suggests a specific location that can be identified on a map. In the case of Voyager 2, no such place exists. The spacecraft is not travelling toward a selected star, planet, or nebula. It follows a trajectory established by its launch from Earth and by the gravitational encounters that occur during its passage through the outer planets. Once those encounters are complete, the spacecraft simply continues forward through interstellar space. Scientific calculations can estimate future positions with considerable accuracy over long periods. These projections indicate that Voyager 2 will experience distant passages near certain stars during the coming hundreds of thousands of years. Yet none of these stars represent a true destination. The spacecraft does not stop, but it does not enter orbit, and it does not settle into a new system. It continues onward after each encounter, carried by momentum through the vast spaces separating the stars. The most accurate answer to the question of where Voyager 2 will ultimately go is that it will remain within the Milky Way for an extraordinarily long time. The spacecraft lacks the speed necessary to leave the galaxy. The gravitational structure of the Milky Way influences its motion just as it influences the motion of stars and interstellar clouds. Voyager 2 therefore remains a tiny participant within the larger galactic system. Over millions of years, the local stellar neighbourhood changes dramatically. Stars move along their galactic orbits. New stars form from collapsing clouds of gas. Other stars exhaust their fuel and evolve into different states. The arrangement of nearby stars visible today gradually disappears. Voyager 2 travels through an environment that is constantly changing, even though those changes unfold slowly from a human perspective. The spacecraft itself may persist through much of this evolution. Interstellar space contains little material capable of causing rapid destruction. Tiny impacts accumulate gradually. Exposure to radiation continues, materials age. Yet these processes operate slowly. The structure of Voyager 2 may survive for immense periods compared with the duration of its active mission. The Milky Way also changes on larger scales. Spiral arms evolve, gas circulates through the galactic disk, stellar populations migrate. The galaxy remains dynamic rather than static. Voyager 2 experiences these changes not as dramatic events but as gradual alterations in the environment through which it travels. Astronomers can project certain aspects of the galaxy's future, but uncertainties increase over longer timescales. The motions of stars can be estimated. Large-scale galactic processes can be modelled. Yet precise predictions become increasingly difficult across tens or hundreds of millions of years. Small uncertainties accumulate. Future encounters become harder to define. Observations indicate likely paths and probable outcomes, but it remains uncertain exactly which regions of the galaxy Voyager 2 will traverse over the most distant intervals. The concept of a last place becomes even more challenging when viewed against the full future of the cosmos. The spacecraft may continue orbiting within the Milky Way for periods far longer than human civilization has existed. During that time, it experiences no destination in the conventional sense. Instead, it occupies a sequence of locations within an evolving galaxy. What is known is that Voyager 2 remains bound to physical laws governing motion and gravity. What remains uncertain is the precise sequence of distant environments through which it may pass over the deepest future. The galaxy itself evolves continuously, and long-term predictions necessarily become less exact as time extends farther from the present. In this sense, the final destination of Voyager 2 is not a star, a planet, or a particular region of space. Its final destination is interstellar existence itself. The spacecraft becomes a permanent traveller moving through the Milky Way. Its journey is defined by persistence rather than arrival. The significance of this future lies not in where the spacecraft ends up, but in what it represents. Voyager 2 begins as a machine built to explore the outer planets. It expands human knowledge of Jupiter, Saturn, Uranus, and Neptune. It crosses the heliosphere and enters interstellar space. It becomes one of the first direct observers of the environment between the stars. Then it continues onward after its scientific mission concludes. Long after the final signal reaches Earth, the spacecraft remains a physical reminder of a particular moment in human history. It carries evidence of a civilization that learns to build machines capable of leaving its home world and venturing into deep space. The spacecraft becomes a silent witness moving through a galaxy far older and larger than the society that creates it. The last place Voyager 2 will ever reach is therefore not a destination that can be marked on a chart. It is the endless interstellar path through the Milky Way itself. The spacecraft moves through the galaxy without expectation of arrival, crossing regions of space that continue changing over immense spans of time. Its journey becomes an ongoing motion through the quiet spaces between stars, a voyage measured not by endings, but by continuity. Within the vastness of the Milky Way, Voyager 2 remains a small and silent traveller, carrying the legacy of Earth into a future that stretches far beyond the limits of the mission that begins its remarkable journey. The darkness surrounding Voyager 2 remains calm and largely unchanged. No engines fire, no new commands arrive, no instruments continue their measurements. The spacecraft drifts onward through interstellar space, carried by the momentum preserved from a journey that begins near a small planet orbiting an ordinary star. Far behind it, Earth continues its own path around the Sun. Generations come and go, languages evolve, nations change, scientific understanding grows. Through all of these transformations, Voyager 2 remains a distant artifact moving silently through the galaxy. The radio signals that once connect it to Earth fade into history. The spacecraft itself continues onward. Around it lies the sparse material of interstellar space. Individual atoms drift through the darkness. Magnetic fields stretch across vast distances. Radiation passes through the galaxy. The environment appears empty, yet it remains part of a larger cosmic system that links stars, clouds, and galaxies together. The Sun becomes only one star among many. It continues orbiting within the Milky Way, carrying the solar system through an evolving galactic landscape. Voyager 2 shares that larger motion while gradually increasing its distance from its place of origin. The spacecraft never truly leaves the galaxy. Instead, it remains a tiny participant within its immense structure. Over immense spans of time, nearby stars shift position, familiar constellations disappear, new arrangements emerge, interstellar clouds evolve, regions of the galaxy slowly change. Voyager 2 moves through these transformations without awareness, following a path determined by gravity and motion alone. The spacecraft does not seek a destination. It does not recognize milestones. It simply continues. The planets become distant memories. The heliosphere remains far behind. Future stellar encounters come and go across timescales longer than recorded human history. Through it all, the spacecraft remains a small object crossing the vast spaces between stars. Its existence becomes a quiet reminder of exploration. Built by human hands, launched from Earth, and guided through the outer solar system, Voyager 2 carries a record of a civilization reaching beyond its home world. Long after its mission ends, the spacecraft continues the journey. The galaxy stretches around it, immense and ancient. Within that vastness, Voyager 2 moves onward through the darkness, not toward a final harbour, but along an endless interstellar road.